Hey everyone, welcome back. So in the last video, we saw how to calculate the autocovariance or the autocorrelation function from an observed data set. And in this video, we shall take a look at some examples where we will be estimating ACF from a data set. So first we look at a simulation where we'll generate our own data set and study some of the things about the ACF. So specifically, we will run an experiment in which we shall compare the sample ACF with varying sample sizes to the theoretical ACF, right? So we will be seeing how good is the sample autocorrelation function by comparing it with the actual values. So first toss a coin and then we have a variable. Xt is 1 if we get a head and 0 if it is a tail. So on the first toss we'll get x1 is either 1 or 0, then on the second toss x2 will be either 1 or 0, and so on. And then define this time series yt in this particular fashion. We will then compute the theoretical autocorrelation function of yt. Then we'll generate a data with varying sample sizes, 10, 100, and probably some more sample sizes as well. And then we'll obtain the sample estimates from each of these different samples. And then finally, we will compare them to this, the theoretical autocorrelation function. So let's start with the calculation first. So you can show that expected value of xt is 0. We can calculate the variance and we can show that it is 1. So these are very basic calculations, but I have them here in case you have any questions about it. So variance of y3 we can show is just 1 plus 0.7 squared. So remember, the constant doesn't make a difference. Xt's are independent. So variance of yt is basically variance of xt plus 0.7 square variance of xt minus 1, but in the second part we show that it is 1, and that's how we get this third statement. Then we can show that covariance between yt and yt minus 1 is minus 0.7. If we look at yt plus k, where the distance is more than 1, where the distance between the 2 points is more than 1 unit, then we can show that the covariance is 0. Basically, then the two terms will have nothing in common, and that's how it will be 0. So I won't go through the details of all of these calculations. So finally, we can, so we have this, right? So we can summarize 3, 4, 5. So autocorrelation function is 1 if there is no lag, is the covariance, which is minus 0.7 divided by the variance, which is this, right? So it's minus 0.47 if you're either a time point ahead or behind, that is the difference is plus 1 or minus 1, and 0 for anything else. So this is the autocorrelation function. And then we shall now generate different samples with different sample sizes. So this is the R code. It is fairly simple. So in the first case, I have sample size 10. I generate this binomial data set. Note that I have an extra point here, and that's because of this relation between, so you see, so yt is xt and xt minus 1. So I need to go like a time step back. So I'm pretending that I'm starting from x0 basically. So to go back to the simulation, so that's why I created an extra x point here. And so y10, so I have added these sample size to the numbers to help us make sense of the plots later on. So the data is generated in this way. So same thing for sample size 100, 5,000, 10,000. And this is the code for plotting all of the autocorrelation functions. So these are the results. So for 10 sample size, that series y10, you can see that if H is 0, autocorrelation is 1. If lag is 1, then it's somewhere around minus 0.5. If you think back to the theoretical one, this is close enough, but these two should be 0 and these are not 0. And these blue lines basically indicate that if this tick, right, if this autocorrelation, if this tick goes beyond this line, then it is significant. That is, it is non-zero. So right now, what it is saying that this one, this minus 0.5, this and this, all of these are not significant. That is, we can all consider them to be, basically we can consider that the autocorrelations are 0 except for the first one here. So this blue line kind of behaves like a p-value in the sense, in terms of how we interpret it, okay? It's not probability, it's not p-value at all. So here in the second one, this first one goes beyond the blue line. This is significant. This is correlation 1. The second one also extends beyond the blue line. So this is a significant correlation. And you can see the values around minus 0.5. And now these ticks are pretty small. Also, the blue lines are much narrower. Here they are wider. Here they are narrower. That's basically because we have a larger sample size. Okay. And you can see that as I increase to 5,000, things look more and more accurate. This is pretty much 0. The blue lines are also really close to each other. And then for 5,000 and 10,000, it at least visually seems the same. So basically, there is some value to having a larger sample size, but maybe after 5,000, it doesn't make much of a difference. Like there's a huge difference from 10 to 100 and even 100 to 5,000, but after that, not so much. So next we'll take a look at one of the data sets that we have discussed earlier. So that's the speech data set. And this is the plot for the speech data set. You can see that it has these repeating recurring patterns, right? So now I'm going to plot the autocorrelation function for this data set. This is the autocorrelation function. So you see that this also has this periodic pattern, right? Basically, the periodicities in this are reflected in this autocorrelations, basically. So what is this saying? This is saying that for the first few lags, we have positive correlation. Then we have some negative correlations. So you can see that there is a big peak around here. This might be about lag 100, 110 perhaps. So if you see at this 0, and then again after about a little over 100 time points, we have these peaks. Similarly, if you look at these peaks, these occur roughly at about, lag of 100, which is probably what is reflected here. So this reflects a lot about the structure, okay? So just to take a look at the numbers, okay? So you can use the autocorrelation function. So if you do plot is equal to false, it will actually give you the values. So autocorrelation 0 is 1. Then for the first 4 time points, it's positive, but it's decreasing. You can see that. Then it is negative, and then the magnitude increases and decreases and so on. So you can see the actual numbers here. So there will be a follow-up assignment in which you will write your own ACF function. So the function will output these values basically. So this will give you a better idea of how this calculation or how this works. So like we have the autocorrelation, we have the cross-correlation function, right? In many data sets, we observed not just one time series, but multiple time series. So we then need to look at their cross-correlation. And it's quite similar. The estimator for cross-covariance is quite similar to the autocovariance. Okay, so remember our notation gamma xy h. Xy means that there are 2 series, so that's the cross-covariance, and h is the lag. And this is the formula. And for cross-correlation, we just have the cross-covariance by the standard deviations, okay? So the formulae are quite parallel to what we've done before, so I won't spend much time discussing this. We'll take a look at an example though. So remember the Southern Oscillation Index, or the SOI, and the recruitment data set. So that's the data set. So this is basically, I think SOI reflects the air pressure changes, which reflects the surface temperature of the ocean. And this recruitment is basically the number of new fish. Okay. So we have two time series. So we have this autocorrelation for SOI, autocorrelation for recruitment, and this is the cross correlation function. So again, there is a periodic pattern, temperature goes up and down, summer, winter kind of thing. So that is reflected here. There is some kind of periodicity in the recruitment as well. Things go up and down, and you see some of it here. So here we see like a really nice pattern forming. So let's see what's going on. So 0, 1, 2 is basically a year. So this is year 1, this is 2 years, 3 years, and so on. So it makes sense that for each year, right, or each multiple of a year, there is a significant positive correlation, and that makes sense because my summer temperatures from this year, or say March temperature from this year, March temperature from next year, are all correlated, or the December temperatures are all correlated. So it makes sense that all of these multiples of 1, there is high correlation. And then it also makes sense that somewhere between 6 months or 1.6 months, 1 or 2.5 years, so half a year, 1.5, 2.5, that is negative correlations, right? So if I look at data in, say, summer and winter, there would be negative correlations. So that's what you see here. So looking at the cross correlation, there is this strong dip here, and you see that the lag here is so this is again yearly data, so this is somewhere at a half-year mark, so basically like 6 months. So what this says is that there is negative correlation between SOI and recruitment. So basically, if my SOI, that is the temperatures, increase today, then 6 months later the number of fish would drop, or if my temperature or vice versa. Okay, so there is a lag effect here, right? So basically whatever happens, the changes in SOI are reflected in the number of fish 6 months later. So do go ahead and read up on both of these examples. The textbook discusses this in a little bit more detail. So it's a good idea to take a look at that. So that is all for this video, and this also marks the end of chapter 1 from the textbook. Next, we will proceed to chapter 3, which talks about more complex combinations or more complex models like the ARIMA model. So far we have studied the autoregressive and the moving average models. In chapter 3, we will be combining both of these in different ways. So that's all for today. I will see you in the next video. Bye.